Yeah, previously we studied the Ising model. It's a spin up and spin down simple system. And here we are dealing with the Ising model in terms of mean field theory. Mean field theory of the Ising model. Mean field theory is widely used in statistical mechanics and in condensed matter physics. And the mean field theory is a general and widely accepted theory. And if some order parameter, here we define the order parameter, and the order parameter is the can be expected as a thermodynamic average value, and the other things we can deal with the fluctuation and the perturbation, whether like variation with the temperature, whether magnetic field. The variation can be regarded as a fluctuation, and the real value we treat as a expectation value, whether thermodynamic average, like that. And anyway, in the mean field theory, we consider for n magnetic atoms are located on a regular lattice. From the Heisenberg model, the exchange energy interaction on the magnetic field can be written down as a Hamiltonian minus j for summation ij sigma I sigma j minus h for sigma I. The first term is the Heisenberg model exchange energy, and the second term is the magnetic field. And here, h is magnetic field in unit of energy. Unit in energy. Spin is the spin. There are two spin, plus 1 and minus 1. At low temperature, at T equals 0 and finite magnetic field, and the spin alignments, spins are aligned along the magnetic field direction. And for at high temperature and finite magnetic field, spin random orientation, and spins are randomly oriented. By maximizing entropy. We call it is paramagnetic state. At low temperature, the state spins line is the ferromagnetic and antiferromagnetic spin ordering, and therefore there is a phase transition. Phase transition at T equal Tc. Here, I say that in mean field theory, we consider the order parameter can be regarded as a thermodynamic average. In this case, in magnetic materials, the magnetization is the order parameter of magnetic materials. And magnetization is regarded as summation average of the identical spins, and this is magnetization is an order parameter of magnetic materials. What is order parameter? Order parameter distinguishes the phases from ferromagnetic to paramagnetic, and in ferromagnetic system, the order parameter is magnetization, means that magnetization with temperature at Tc, and the magnetic moment, magnetization evolves in the ferromagnetic system in magnetic materials, and it is a finite value, and magnetic moment equal to 0 in paramagnetic system on the without magnetic field case. And therefore, then this kind of order parameter distinguishes phases and ordered state or the random spin state. And in a phase transition from the gas to liquid, what is the order parameter? In that case, the order parameter is the compressibility, because liquid is the uncompressible and the gas is compressible. Therefore, compressibility distinguishes the gas and liquid. Therefore, compressibility is the order parameter from the gas to liquid phase transition, like that. And anyway, all of the phase transition accompany the order parameter. Order parameter distinguishes the phase transition from one phase to the other phase. And here, let's consider for the particular spin. Consider a particular spin sigma 0 at site 0. In the origin, let's consider for the particular spin sigma 0. In this case, the Hamiltonian, let's write the Hamiltonian. In this case, because one spin is minus sigma 0. Sigma 0 is constant, and also J value, and for Ij becomes J, because for I spin is set to 0, and also plus H, and also summation for we specify the spin at site 0. In this case, then how to deal with the mean field theory is that we can modify this term as the minus sigma 0, and anyway the summation we can write down as the minus write down gamma jm plus h minus sigma 0 j, summation for j, sigma j minus m. Now here, minus m means that it is a thermodynamic average, like this. Here, in this case, the sigma 0 here it becomes the m, and mathematically this term and this term cancel with each other, and because the summation for j, there are gamma coordinate. In gamma means that nearest neighbor coordinate, number of nearest neighbor coordinate, and therefore this term, the blue line term, can cancel with each other. And also it is identical with identical to the first term. And anyway, therefore, but the important thing is that it is we can regard the second term. Why do we write down this one? And it is a fluctuation, mean field Hamiltonian. It is a mean field Hamiltonian. It can regard it as a fluctuation. A fluctuation term, because as m means that thermodynamic average of a spin, and sigma j is that the other spin. Therefore, it is a spin fluctuation, and the first term is a genuine magnetic moment with applying magnetic field term. Therefore, we deal with the magnetic moment with applying magnetic field and plus a fluctuation term. And here, therefore, here let the m is that sigma 0 and sigma j are thermodynamic average is identical with each other. And therefore, from the how can calculate the thermodynamic average of the sigma 0 is that trace exponential minus beta h trace sigma 0 exponential minus beta h sigma 0. It is natural from the canonical ensemble, and trace means that summation in the diagonal. If actually in quantum mechanics, h is in general, h is not a quantity but a matrix, and therefore matrix formalism it means to diagonalize, and the diagonal term summation we call it as a trace. Therefore, trace exponential minus beta h means that here exponential minus beta h is the Boltzmann factor, and the trace of the Boltzmann factor it is a partition function, and trace sigma 0 exponential minus beta h is the it is natural representation for the average value of the sigma 0. Therefore, we know that sigma 0 is like this, and also here sigma 0 we set sigma 0 average. Then in this case we can consider as the sigma 0 has a plus minus 1. Therefore, it is exponential minus beta h for sigma 0 equal to 1, and plus exponential minus beta h for sigma 0 equal to minus 1. There are two possibilities for spin up and spin down state, and also here spin up's case exponential minus beta h sigma 0 equal to 1. In the spin down case, sigma 0 is minus exponential minus beta h sigma 0 equal to minus 1. Therefore, h means that from the above, here the fluctuation in thermodynamic average, the fluctuation can be cancelled. It can be it is very small in the fluctuation. The thermodynamic average we can regard it as a 0. Therefore, it is exponential minus minus plus sigma 0 is a plus 1 beta gamma j m plus h plus exponential minus sigma 0 is minus 1. Therefore, from the above from this and the minus beta gamma j m plus h. Here in the numerator, exponential beta gamma j m plus h. here minus exponential minus beta gamma jm plus h. It is a hyperbolic tangent hyperbolic beta gamma jm plus h. This is a solution from the mean field theorem, mean field equation of the Heisenberg exchange energy. And therefore, when you look at this equation, this magnetic moment is order parameter. We should solve the magnetic moment, but in the right hand side also have the magnetic moment. Therefore, it cannot be solved analytically, and we should solve by numerical calculation. And anyway, and from the iterative method is one of the method, but the graphical solution is another method. And anyway, here let's assume that we think about the extreme cases for several cases. The first case is for zero magnetic field case for h equal to 0 case, and there are second possibilities. One is that m equal to 0, and the other one is that positive magnetic moment plus minus m0 in the case of the beta j gamma is greater than 1. And also second case is that t equal to 0. T equal to 0 means that beta is infinity. Beta becomes infinity, and hyperbolic tangent is very in the hyperbolic tangent x. Here, if the x is very large, the hyperbolic tangent beta gamma jm should have the plus minus 1 in the extreme limit. Therefore, m0 is that m0 reaches to the plus minus 1, and 0. There are two possibilities. And so in third case, as t is close to tc, and the hyperbolic tangent can be expanded as a Taylor series, and also therefore m0 is that beta gamma jm minus 1/3 beta gamma j cube m0 cube plus higher order term, and therefore m0 can cancel with each other, and therefore m0 square as a function of temperature is that beta gamma j to the cube 3 beta gamma j minus 1. Here let the beta gamma j is that gamma j over kbt, and therefore it is a dimensionless. Hyperbolic tangent should have the dimensionless argument, and therefore here the TC is that gamma j over kb is the TC. It is a temperature. It is a dimensionless quantity. It is reasonable. Therefore, in this case, from the above equation, then the m0 means that the magnetic moment at Tc, and also plus minus square root to 3, and also T over Tc to the 3 half, and also here Tc over T minus 1 to the 1/2. Therefore, it is from this equation, and at near Tc, m0t is proportional to the Tc over t minus 1 to the 1/2 as t close to Tc. Yeah, it is a solution near Tc, this value. And anyway, this can be calculated by the numerical solution method. And this solution, we assume that here, like this, and we know that magnetic moment, let's write down, let's copy. M equal to like this. It is a solution from the mean field theory. And also here, we can write we can solve this problem as a graphical solution. From the graphical solution, in the right side, and there is a y1 equal to m, and left hand side is y1 equal to m, and the right hand side y2 equal to hyperbolic tangent. And anyway, beta gamma j is that tc over t m, like this. When you draw a graph of the hyperbolic tangent, is that there without magnetic field, h equal to 0 case, and here I'm sorry, it is a hyperbolic tangent function, and here it is, for example, it is t lower than Tc for increasing temperature, and the value is like this for t equal to Tc case, and for increasing temperature, the magnetization also decrease, like this. This is x-axis magnetic moment. In y-axis is y1 and y2, and here, and y1 shows that it is a linear shape, and for example, like this. It is that there are two solutions. I'm sorry, it is a little bit different, and that there are two solutions. It is red one is y1 equal to m, y1 equal to m, and the black one is the hyperbolic tangent function and the y2 function. And therefore, from the graphical solution without magnetic field, there is a finite magnetization value, for t lower than Tc. And anyway, for here, for t equal Tc case, the intercept between the red one and this black one is that the 0, like this. There is no spontaneous magnetization, but below Tc there is a finite spontaneous magnetization in the even 0 magnetic field case. But in the positive magnetic field, when you apply the positive magnetic field, and there is a negative shift in this one, and therefore the t equal Tc should have like this, and the t less than Tc, and at t equal Tc, like t equal tc case. So t is greater than tc, like this. T is greater than tc. In this case also, why is that? Yeah, like this. Therefore, in this case, there is a finite M0 case, but in other there is no negative magnetic moment, but finite magnetic moment for applying magnetic field, positive value. Well, negative value is that and it shifts to the right hand side, like this. And if we go t lower than tc, I'm sorry. You go t equal tc, for low one, like this. For t greater than tc. Also, for negative magnetic field, I'm sorry. Also shows like this, and here, when you apply magnetic field in the negative field, there is a negative M0, negative M, but there is no positive magnetic moment. It is a graphical solution of the magnetization. And next, we will see that anyway, this kind of Ising model is we deal with the mean field theory, and from the mean field theory, the solution is like this: hyperbolic tangent. The real solution is like the hyperbolic tangent, but it is that M and M implicit argument. There is an implicit argument of magnetic moment, and therefore we should solve this problem as the graphical solution. But in the near TC, T equal to TC case, is that magnetization, spontaneous magnetization, can be represented like this.